So in this video we're going to talk about electricity and the conservation of energy. Remember when we did mechanics, we could do free body diagrams and deal with forces and then find accelerations, but sometimes it's easier to do conservation of energy, kinetic energy, potential energy, and so on. We're going to find the same thing with electricity. So the first thing, if I have two charges here, they're two positive charges, and I'm holding them, they want to fly apart, and if I'm holding there's some energy stored in there, so that's going to be potential energy. So we can calculate the potential energy using this equation, Q1, Q2 over R. Now, the nice thing about this is that energy is not a vector. So we're not going to deal with arrows or angles like we have to do with electric fields, so that makes it a little bit easier, but we do have to watch our signs, or negatives or positives. I'm kind of lazy with my signs maybe when I do force stuff, but I have to be very careful when I'm doing potential energy. So here's an example. I have a proton at distance 4 meters away from a fixed metal sphere that has a charge of 3 microcoulombs. I'm going to make a little sketch. I have my sphere here. It has a charge of 3 microcoulombs. Over here I have a proton, and the distance between them is 4 meters. And there's going to be potential energy in there because that proton wants to fly away, and if I'm holding it there and it can't, there's some potential energy stored. So for 1, we're going to find the potential energy, and it's KQ1 Q2 over R. So K is 9 times 10 to the 9. Q1 might be the 3 microcoulomb charge, and we have to remember micro means 10 to the minus 6. And then the second charge is the proton, and we have to remember the charge on a proton is 1.6 times 10 to the minus 19. And then we're going to divide that by the distance, which was 4 meters. And we'll end up with a potential energy of 1.08 times 10 to the minus 15 joules. Now, step 2, if protons allowed to repel from the sphere, what will be its kinetic energy when it's 10 meters away from the sphere. So I'm going to let it go. It's going to start moving away, and the farther away it gets, the less force there's going to be on it. It's going to be easier to hold it there, so there's going to be less potential energy. So I'm going to find at 10 meters, I'm going to find the PE for that. So it's going to be KQ1 Q2 over R again. So 9 times 10 to the 9 times 3 times 10 to the minus 6 times 1.6 times 10 to the minus 19. Divide that by, now my due distance is 10. When I do that, I get a value of PE equals 4.32 times 10 to the minus 16th joules. Now, it wasn't asking me for the potential energy there, it was asking me for the kinetic energy. I'm going to use conservation of energy to find that. I'm going to say that E total when I was at 4 meters is going to equal the E total at 10 meters. Now, so that's going to be the potential energy plus the kinetic energy at 4 equals the potential energy plus the kinetic energy at 10. Potential at 4 was 1.08 times 10 to the minus 15. Now I was holding it at 4, so it had no kinetic energy, equals potential energy at 10, we just found was 4.32 times 10 to the minus 16. And we're trying to find the kinetic energy at 10. So now I would just subtract the 4.32 times 10 to the minus 16 from both sides. Cancel off over here, and on this side I'm left with kinetic energy, and over here I'm going to have a value of 6.48 times 10 to the minus 16 joules of kinetic energy. Then in part 3, what will be the speed when it's very far distance away? So we're meeting us along here. We just found the kinetic energy. We know when we're looking for speed. So KE is 1/2 mv squared. So our 6.48 times 10 to the minus 16 makes 1/2. Mass of the proton, we can look up on the reference table if we don't have it memorized yet, is 1.67 times 10 to the minus 27, and then v squared. If I solve that, I'll end up with a velocity of 1.14 times 10 to the 6th meters per second. All right, now we're going to start talking about something called electric potential. And electric potential is V, there's a letter for it, and the unit is volts. So it's actually not potential energy, it's something different. And I'm going to give you a couple equations here. The change in potential energy, which can equal the work done, is going to be Q times the change in voltage, and the V is KQ over R for a single point charge. And I'm going to make a little note here, okay, that force is equal to E times Q. All right, so if I take the electric field multiplied by Q, I get force. It's going to kind of be the same thing. The potential energy would be equal to the voltage times Q. And that's kind of where this is coming from over here. So voltage is the potential energy as electric field is force. So voltage is kind of a hard thing to define, just like electric field is. You can't see it, but you can use it to define energy, just like you can't see an electric field, but you can use it to define force. Now, another unit is electron volts. So first we're going to do an example up here. We'll do how much energy is required to move an electron across a potential difference of 9 volts. So that'd be basically like a 9-volt battery. How much energy are you going to get moving one electron across it? So this here potential difference, that's telling me delta V, right? V is potential, the difference is delta. Delta V is 9 volts. So then I'm going to do work or energy is Q delta V. Q is 1.6 times 10 to the minus 19 coulombs. That's the charge on an electron. And then delta V is 9 volts. And I end up with 1.44 times 10 to the minus 18th joules. Now, you'll notice I multiplied coulombs times volts. So I'm going to make it over here that 1 coulomb volt is equal to 1 joule. Okay, a joule can be defined as a coulomb volt. The reason I'm making a point of that is there's another unit. There's an electron volt. To get electron volts, you use the same equation, but you leave Q in E's. All right. So I can do the exact same problem. I would do W equals, and instead of saying for the charge of the electron, I'll make a note over here, Q of an electron equals 1E equals 1.6 times 10 to the minus 19. Instead of converting to coulombs, I'm going to leave it in E's. So it would be 1E times 9 volts. All right, and I would get 9 electron volts. That's an acceptable form of energy. I couldn't use that then in 1/2 mv squared for KE or something like that, because it's not the rate, it's not in joules. But if it asks for energy, I can write the energy in electron volts and be done with it. I like to say this is kind of a lazy person's way of finding energy, right? I could do this equation here and end up with 1.44 times 10 to the minus 18 joules. That's true, that is the amount of energy, but if I want to be lazy, I can just do 1E times 9 volts to get 9 EVs. It's a lot quicker. So that, I think, is where that came from. They're equivalent. 9 electron volts is the same as 1.44 times 10 to the minus 18th joules. Both answers are correct if you're looking for work done. But if you're going to go farther than that and calculate something like velocity, then you're going to have it in joules. So here's an example. An electron is taken across a potential difference of 100 volts. What's the energy in joules and in AVs? So energy, we use W for energy. So then it's going to be W equals Q delta V. I can say it's 1.6 times 10 to the minus 19 coulombs times 100 volts. And that would give me 1.6 times 10 to the minus 17 joules. Completely correct and is the right answer. Or, if I do it in these, W equals Q delta V equals Q is 1 E for an electron, delta V is 100 volts. So the work done is 100 EVs. Also a correct answer. Now here's another one. A point charge of minus 2 millicoulombs is located at the origin. What is the electric potential of point P, which is 2 meters away from the particle? All right, so I'm going to draw a little sketch over here. We have our minus 2 millicoulomb charge over here. Over here we have our origin. This is 2 meters apart. And this is going to be like finding electric fields, except for we don't have to draw any arrows. All right? So for step 1, we're going to find the electric potential. Electric potential is V. Find it by doing KQ over R. So 9 times 10 to the 9th. The charge is minus 2 times 10 to the minus 3rd. Divided by my distance is 2. And I'm going to end up with minus 9 times 10 to the 6 volts. Now, I didn't have to worry about direction. Okay, I didn't have to draw arrows, but sign is very important. Negative charges give me negative voltages around them. So this voltage is negative. So I'll just make a note of that. Voltage and the negative. So it's important to keep the sign. Step 2, the electric potential at a distance of infinity. V equals KQ over R. That's going to give me an infinity on the bottom. When I divide by infinity, I get 0. So the electric potential, no matter what my charge is always going to be 0 at infinity. And then what is the change in energy for a plus 4 microcoulomb point charge, which starts at infinity and moves to point P? Now, I could calculate this using that potential energy formula, but I think it's going to be easier to do this. Change in energy is W. So I do W equals Q delta V. So, our Q that we're moving, now this Q we have to do, it's the change in energy for this charge. It's not for the 2 microcoulomb charge. That one's not moving. It's not going to have a change in energy. I want the change in energy for the plus 4. So it's going to be 4 times 10 to the minus 6 coulombs. Okay? Now my delta V, I'm going from infinity to point P. So V, change in V, is going to be from 0 to negative 9 times 10 to the 6th. So my change is delta V is equal to minus 9 times 10 to the 6th. So minus 9 times 10 to the 6 volts. If I multiply coulombs times volts, I get joules. So my answer is going to be in joules. And this is going to give me minus 36 joules. And it's minus because this proton, if it starts very far away, it sees this negative charge, it wants to go towards it. So it's going to go on its own from infinitely far away and move towards it on its own. So you don't have to do work on it to get it to do it. It wants to do it. So that's why it's negative.